Welcome everyone to Enhancing Environmental Monitoring with Real-Time Data Integration. This is going to be presented today by Dusty Worth from 1898 & Co.
So real quick, kind of a quick agenda, going to step through the introduction, the challenges and our solution to it, talk about some issues that we encountered and some mitigation strategies for those, and then a quick conclusion. So quick introduction to me. I have 18 years in environmental permitting and GIS. Just started with FME fairly recently, about 3 years ago, but I've been all in ever since. Worked with clients across multiple industries, but largely focused on utility sectors, but working for an engineering company, get a pretty broad breadth of experience there. So real quick project overview. This was for a new manufacturing facility expansion. They were struggling to get their ambient air monitoring permit. The project was actually delayed almost a year by that permit. And so we stepped in and came up with a solution for them to allow them to do real-time monitoring of it, which allowed the agency to go ahead and issue the permit and allow them to move forward with it. And so our solution was a combination of FME Form, Flow, Survey123, ArcGIS Online, an Experience Builder dashboard, and then ArcGIS Insights. So the problem, this was a $300 million EPC or engineer procure construct project for us. The permit was, as I mentioned, was delayed due to the particulate matter 2.5 and 10 pollution in the area. So to expedite it, the client agreed to do this real-time monitoring. I don't think anybody actually knew what they were agreeing to when they did. So kind of a quick question for you guys. How many of you have dealt with like construction teams, construction foremans, anything like that? Okay, a few of you. So imagine if you went to the construction foreman for this large of a project and you said, okay, we agreed to get this permit, but every 15 minutes you're gonna have to log into 2 different systems, run 2 calculations, compare them to the spreadsheet, decide if you're going to do something, and then document it all. And that's every 15 minutes throughout the day. So it's probably going to take you 15 minutes. So that's basically going to be your job. So that's what they had originally agreed to. So obviously the construction team was not too happy with that, and they said there's got to be a better way. And that's when they came to us. So then in comes FME. So FME was really the solution that allowed us to implement this and meet all of our requirements so that they didn't get shut down. So what we ended up doing is we deployed a network of field sensors on the site, did some real-time data processing, and then integrated all of those different technologies, the ArcGIS Online, Survey123, Insights, all of that. So a little bit more in depth on it. So this is actually a picture of one of the sensors on the site there on the right. So we deployed 4 different PM monitoring stations, and they're through a company called QuantAQ, Each one has their own solar panel for power, so they're independent. They each have a cellular modem, so they report back automatically. And then we also had one weather station on site because we needed to measure both the humidity and the wind direction. So we strategically placed the sensors at each of the cardinal directions on the edge of the property, and that allowed us to help out with some of the processing that I'll get into here in just a minute. We also had to deploy these 60 days prior to the start of construction so that we could collect the historic data, because what we had to do is we had to develop the baseline for the ambient pollution in the area so that we knew what our action levels were to trigger events. So with the real-time data acquisition, we used FME Form to create the workbenches and then publish them up to Flow. So every 15 minutes, the Flow would trigger and pull down the last 15 minutes worth of data through the QuantAQ API, run some calculations. So we had to do a calculation of a rolling hourly average as well as a percent change. So we had 2 different triggers. So if the percent change went over or the rolling hourly average went over a certain amount, we had to trigger some sort of action by the construction crew. The threshold monitoring, like I said, we had the predefined values from the ambient that set those, and then we integrated it all back into AGOL for data reporting, because we had to be able, if the agency showed up on site, we had to be able to export out all of our data tables showing what the values were at every 15 minutes throughout the day, and if any action had been taken and what that action was. So that was part of it, is we wrote all of that data back to an AGOL data table so that it was easily accessible through the dashboard. So this is just real quick. This is part of the workbench that we developed, just doing the API calls there to pull it in, some data validation. And one of the things that I'll talk about later is we ran into a little bit of an issue with data lag with the cellular modems and the API processing. So we had to do some kind of unconventional data processing and data validation in here to get it. Then real quick, this is the flow automation that we had that triggered every 15 minutes. So we have several email triggers on there. So we were checking to verify that all of the sensors were online and reporting in. If not, we would send an email out to the construction crew and say, hey, you need to go check this one, see if the battery died or the modem died, or as happened a couple of times, kids in the local area took a bat to them. So we had some error checks in there to make sure that everything was online. And then also up at the top there, that's the action email that went out if they needed to do something. So this is kind of a screenshot of one of the emails that we sent out for a notification. So we integrated it both with the dashboard and a Survey123 form. So there's several different actions that they could potentially take. And so the Survey123 form was developed to have them just answer some quick questions about what's going on the site, and then it recommends the action that they have to take. And then ultimately it was up to the construction crew, so they could choose to take action or not. But the last question is what they implemented, or if they implemented anything that reported back to ArcGIS Online. If they chose not to do anything, then the next 15 minutes, if they were still in exceedance, they'd get another email. So it was kind of pestering them until they actually did something. But once they did do it, then it shut down the emailer for 2 hours. So that way they weren't, as long as they were in compliance, they didn't continually get pinged with emails there. So this is about the AGOL dashboard. So we were able to pull in all of that data since we were writing it back to AGOL and have kind of a real-time sensor status there that they could just have up on their computer at all times and see how things were going. We used ArcGIS Insights to display the historical data for them as well. And so that way they can see like what's been happening over the last 24 hours, not just from the construction, but since it's a full 24 hours reporting, they can see what the ambient stuff is doing. So they may have an idea of how construction would affect it. And then also how it's been going over the last 7 days. So if you don't get rain, as things dry out, your PM levels are going to go up and stuff. And then, as I mentioned, we had to have the ability to export out that historic data in case the regulatory agency ever showed up on site and said, prove to us that you're in compliance. So as I mentioned, we use Survey123 there. So these are some of the examples of the screens there. So just some general questions like, are you actually constructing anything on the site right now? Has it rained recently? Is there anything happening offsite? And depending on how they answered it at the bottom there, you can see that it would say no dust control measures are required this time, or implement dust control measures. And if they got the implement dust control measures, then they would have to answer what they were doing to alleviate the problem there. So the team really liked this because it kind of took the thinking out of it for them, and it was just one click and then a few simple questions, and they could do whatever they needed to do to get that. This here is the Experience Builder dashboard that we had set up. So just some simple readings here. These are the actual values that were recorded for the last hour for each one, whether there's an exceedance, and then the green dots over there would turn red, as well as on the map if they actually had an exceedance down there. And then at the bottom, we have the weather information that was displayed from the weather sensor there. And you can kind of see that over there with the green dots, we've got basically a sensor on each of the 4 cardinal directions. And that helped us out with the calculations. So if like the sensor on the east was picking up an exceedance, but the wind was blowing to the west, you knew that the dust was coming from offsite. So it wasn't a result of yours. But if the one on the east was not picking it up, but the one on the west was, you knew it was a result of what was on site. So we had all of that built into the FME Form too, to kind of do that logic for them, so they didn't have to really do all that much thinking on site. So this was new to me when we did this. This was ArcGIS Insights. It was much easier to do this than natively in Experience Builder to display the past 7 days and past 24 hours, but that's what this is showing here. So past 24 hours on the bottom and past 7 days on the top. And we were monitoring for 2 different PM 2.5 and PM 10. So those are the 2 different lines there, but you can see that they kind of spike throughout the days as you go on. So we did experienced several issues with this. It was a very cool project, but we definitely have some lessons learned and some things that we would do differently. So one thing that I already kind of alluded to was the API or cellular lag time. We never really figured out exactly what it was, but some of the sensors would take almost 10 minutes to populate through to the API, and the others were populating almost a minute after they made the reading. So, and as you can see by that map, they weren't all that far apart, so cellular connectivity shouldn't have been the issue, but we never really figured out what the issue was. We worked with the vendor quite a bit, but so what we ended up doing is we actually delayed our poll by 10 minutes. So that way we could ensure that all of the 15-minute values that we needed were there. Also, as I alluded to, the sensors did go offline from time to time, so we had to build in that logic check there to check that. Sometimes they would just lock up, and as I mentioned, we also had some hoodlum teens take some bats to them. That was an expensive learning, so we learned that they should be on the inside of the fence and not on the outside of the fence. So another technical issue that we had is the weather station that we used. It did have a cellular modem, but it didn't report back, and it wasn't an API. So we had to install a program called LoggerNet on a local machine that would dial into that modem and pull the data. We had a lot of issues with that, with IT pushing out updates to the machine that would reboot it, and then we would lose that data, or we wouldn't have that data reporting. So also with power outages at the building, ended up putting it on an APC, but still had some issues with some of that stuff. So ultimately, I think we would go with an Internet of Things based weather station in the future that actually has an API, so that it's a little bit easier and we can avoid some of those issues with that. So quickly, conclusion, kind of the key outcome and benefits. We ultimately were successful in getting the air monitoring permit and getting the project built without the construction crew having to hire somebody to just monitor it. We successfully integrated all of those technologies for a comprehensive solution. And I really think that this is the wave of the future for air monitoring. It was highlighted by both the state agency and the EPA as a large success. So I think that they're going to be wanting to see more of this in the future. So, and with that, any questions?
Awesome, thank you.
Hello, everyone. Welcome to my talk on editing feature services and FME using the ArcGIS REST API. My name is Daniela Messler, and I am a senior GIS data analyst at TRC Companies. Today, I'll give an introduction to who TRC is, the challenge, the solution that solved that challenge, and a quick conclusion. So now on to a bit about TRC. I work within the intelligent grid solutions sector, and our sector is made up of around 400 dedicated location technology professionals. We provide a number of services from the ArcGIS utility network deployment to modern cloud solutions and mobile products such as Lemur, enabling utilities to work in the field without obstacles. We work with utilities and others to build and deploy intelligent grid solutions, and our assistance enables those utilities to scale for the future, lower costs, increase efficiency in deployment and management. Here are some examples of our many long-standing partnerships that enable us to be successful in this space. As integrators, we are an FME technology partner and have been an Esri Platinum partner for about 12 years. We pride ourselves in conducting the first utility network go-live, and that was for National Grid in 2017. Since then, TRC has implemented 12 utility network production go-lives in the last 4 years. All right, now on to the challenge. So I want to get some context on the need behind the solution. We were working with the largest natural gas distribution company in the US, and had just gone live with a full transformation from legacy data in the geometric network from multiple databases into the Esri utility network, now hosted as a published feature server. At this point in time, we were in the final handoff stages where the users and editors were reviewing their transformed data. And it was in this stage that our client requested some edits. These edits included spatial updates like correcting center lines, adding new features that were intentionally skipped in prior stages, and then adding new attributes to existing features. So in some cases, we had several 100,000 features that needed to be inserted or updated. And given the nature of the edits and the size of the data to be modified, we quickly realized that we didn't have a process for a time-efficient bulk edit to a feature service. And so the Googling began. As is true with many things, it's important to state that there are several ways to accomplish any task, and I'm sure there are many ways to solve this problem, but our team's skills leaned heavily on Esri infrastructure, Python, and FME. So we decided using the ArcGIS REST API inside FME was the best method. The primary documentation reference for this is just the apply edits operation Esri developer documentation. It states that it applies edits to features associated with multiple layers or tables in a single call post only. And the source is a great place to start with any task, but in my research, I thought it was a little odd how I saw very little about implementing this into large editing workflows. So the usage is simple, but the difficulty lied in how to apply the correct JSON formatting to those features. As a short note, also, we did try to use the feature service writer, but ran into timing out issues and slow linear write speeds. All right, so now we're going to get acquainted with the apply edits array structure. These screenshots are just from the documentation for the edits parameter. There are a few more parameters. This is just the one that we needed to use for our case. So we knew we needed a JSON array formatted in this way, with each set of edit operations like add, deletes, or updates grouped by batches, where each batch has a unique ID. And inside each batch, you can submit multiple features in a single go via the edit type array. All right, so then the array also has both geometry and attributes in each portion. And it's also worth noting that the geometry formatting differs for points and lines. So for points, it's a single XY pair, but for lines or other complex geometry, there's an additional paths portion that stores each XY pair in its own bracket. So all predictable, but we needed a way to scale this. So now on to the solution. In this section, I'll provide an overview of an example form workbench. It's important to know the URL, the portal credentials, and the feature service ID. Additionally, as is normal best practice, a version needs to be created for this edit. So as a quick highlight, the upper bookmarks are reading in the feature service, some initial processing. This can be whatever type you need for your edit. The lower left bookmark is the token creation, and then the center transformer is merging that token to each record. And then the lower right bookmark is the JSON array processing and parallelism. And the final bookmark is HTTP caller transformer and error logger. So we begin, read our feature service, conduct whatever edits, get your connect to the feature service by getting it, and then get a token. The real heavy lifting is in the string concatenator transformer. For non-spatial attributes, a very simple Python script was used to read in the fields that we needed and then output a key value pair that was needed for the string concatenator. As a note, you could also do this more dynamically in a Python caller if desired. So the trick here is to copy and paste the output of that key value pair formatting into the set to advanced portion of the transformer. Here, when you go back to the main screen, FME correctly interprets the formatting as the true field value pair with the required colons, parentheses, and brackets. Also notice that the attributes parameter is included at the top as is required by the API. So this is immensely helpful because as with a few feature classes in the UN, some have almost 100 fields. And if you're trying to insert new features, trying to click the constant attribute value is just problematic. It's also in this same transformer, we handle the geometry. So prior to the step, we use a coordinate extractor to get the coordinate pair. We then simply apply the constant geometry parameter and then extracted the coordinates as a value. For the line geometry, the process is the same, but an additional Python caller iterates through all the XY pairs and formats them into a separate bracketed list. So note the extra square brackets again around each pair within the new paths bracketed portion. The output of this transformer is a newly formatted feature named _feature. So at this point in the process, we have our correctly formatted spatial and non-spatial attributes. We then use parallelism to assemble all the new individual JSON arrays into an FME list. These will then be parsed out into separate chunks based on the total number of features to be edited. We then use a list concatenator and attribute transformer to finally assemble our formatted lists of features along with the portal token that we generated in that prior bookmark. So the result of parallelism here is a grouping of formatted records into parsed sets that will become separate but concurrently executed jobs. Finally, we use the text encoder to encode into URL and then use the HTTP caller transformer to submit the edit, update, add calls. In this transformer, we insert our payloads into the upload body box. That's the @value features parameter. You also may notice that our team used FME user parameters to standardize and streamline the edit version name, token, and feature service URL. Also, a quick note, we have a test filter here to filter out if there are any chunks that had a status code that was a failure, and then we could more easily take a look at what was going on there. A quick troubleshooting tip, whether you're troubleshooting adaptations of the call or trying to fix issues with failures due to formatting, it's simple to do singular tests just using the endpoint URL in a browser. The error responses will still be the same, but you can submit a single feature and hone in on the issue more specifically. All right, conclusion. So with FME, we were able to leverage the ArcGIS REST API apply edits operation and parallelism to very quickly process and execute different edit types. The processing time for hundreds of thousands of features was reduced to just a few minutes. Additionally, our team utilized standardized user parameters for easy reusability and streamlining. So in our use case, given the workflow is in the final stages of a migration project, we configured separate workbenches based on the edit operation type, so the client could easily plug and play their feature service endpoints and portal credentials. As a quick note, if bulk edits to a feature service is a task your team is conducting regularly, it may be best to consider the new data virtualization workflow that was introduced this week. That sounds pretty cool. For our use case, we only need to do this phase of work for a few minutes or a few weeks with the client. Like many things, there are several ways to do a single task. The process I just described using FME, the API, and parallelism worked great for us and accomplished our goals. Thank you.